Objective 5.2 asks that you be able to draw a cell, a galvanic cell or electrochemical cell from a cell diagram and vice versa. So in this picture we have an electrochemical cell or a galvanic cell, and this is the cell diagram that goes with this electrochemical cell. So in order to be able to translate this picture into this diagram, we need to understand what this picture is telling us. This electrochemical cell is a setup whereby we can take two half reactions and connect them through an external circuit, a wire, that forces the electrons to flow through an object like your cell phone or your calculator or anything that uses a battery, so that we can do work using those electrons, so that we can use the chemical energy from this electrochemical reaction to actually do work. So that's what an electrochemical cell does for us, is that it uses the chemical energy from a redox reaction in order to do work. So notice that we have these two half reactions, and one of them is called an anode and the other one is called a cathode. Each of the half reactions have a electrode that is conductive, which we can connect our wires to so that we can make electrons flow through the circuit. So the electrode in each of these half cells is different. In this half cell, the anode, we have a zinc electrode, and notice that zinc is part of the oxidation half reaction. The zinc metal is being oxidized to zinc 2+ in solution, and that releases 2 electrons. Those 2 electrons can be conducted, because this zinc metal is conductive, through these wires, through this voltmeter, to the cathode or the reduction half reaction. In this reduction half reaction, we have hydrogen cations, H+, and hydrogen gas. Neither of these two species are conductive, and so we're going to need something to carry those electrons into the solution so they're available to the H+ ions to combine with them in order to make H2 gas. So in general, we typically use a platinum wire to do that. So there's a platinum wire shown here that is going to conduct the electrons into the solution so that they are available for this half reaction. When we have an electrode that is not part of the half reaction, that's called an inert electrode. Okay, so we have an anode and we have a cathode. At the anode, that's where the oxidation half reaction occurs. It's the anode because electrons are being produced, and so this electrode is going to be negative in nature because we're producing electrons, and the electrons are going to move away from that negative charge towards the cathode, which will be positive in nature because we're going to be using up electrons in this half reaction, so we're going to be removing electrons, leaving a positive charge. So I always remember this as anode for oxidation, and anions are negative, the anode is negative. Cathode for reduction, and the cathode is positive, and cations are positive. And that's how I remember which is the anode and which is the cathode. So if we just transfer electrons merrily along our way, this side will become more positive and this side will become more negative because we're transferring electrons over to here, we're transferring electrons over, taking electrons away from here. And if we have a charge differential, pretty soon the electrons are going to stop flowing because now there's too much negative charge over here and the electrons are going to be repelled from that negative charge. And so we need a way to balance out the charge, and so we use what's called a salt bridge. The salt bridge is filled with an electrolyte. An electrolyte is just simply anything that produces ions in solution. And if we allow those positive and negative ions to flow, then we can put positive ions over here to balance the negative charge that's building up, and we can put negative ions over here to balance the positive charge that gets built up. And that way the charges get equalized so that each of these solutions is neutral overall in charge, and the electrons can continue to flow through the outside circuit without having resistance from an extra buildup of negative charge over here. Okay, so now that we understand some of the terminology involved in electrochemical cells, let's see how we can translate this picture into this diagram. So what we're going to do is we're going to start at the anode, and we're going to write the chemical symbol for the anode on the far left of our diagram. And then the chemical symbol for the cathode is going to be written on the far right of our diagram. Notice that what we're writing is the actual conductive species that is going to conduct the electrons from one cell to the other cell, one half cell to the other half cell. Then we're going to work our way inwards from the electrode towards the salt bridge. So we look at what is in contact with that electrode. And what's in contact with that electrode is a solution which contains the zinc 2 plus that's part of the oxidation half reaction. So we're not so much worried about the other counter ions or spectator ions that are in solution, but only the ions that are important for the oxidation reaction. We're going to separate our anode, zinc solid, with a solid line from the species that are in solution. That solid line says that there is a phase boundary between the solution and the solid electrode. So we go from solid to solution, and there's a change in phase. Solid, liquid, change in phase. And so every time we see a vertical line, that means that there is a phase boundary in our half cell. So if we keep working our way towards the salt bridge, at this point we've accounted for all the species in the half reaction, and so now we're at the salt bridge, and we represent the salt bridge by a double vertical line. So the salt bridge is represented by that double vertical line. Now we're over in the next half cell, and so we work our way towards the cathode electrode, and what we have first is a solution which contains H+, and so we're going to designate that we have H+ in solution, and we can show the concentration of the H+ in solution if we want to. That's optional, but oftentimes it's helpful to give the concentration of the ions in solution if you know them. So we have H+ in solution at 1 molar concentration, and then there's another phase boundary here because the H+ in solution is in contact with hydrogen gas that's being bubbled through the solution. So there's a source of hydrogen gas that's being bubbled through the solution, and we see the bubbles here that represent the hydrogen gas. So there's a phase boundary between the gas bubbles and the liquid solution. And so we're going to represent that by this vertical line, saying that there's a phase boundary here. And then at that point, we have designated all the species in our half reaction, on our reduction half reaction. And so we just have the platinum, which is the cathode electrode that is going to be the source of electrons for this reduction half reaction. As we all know, electrochemical cells, batteries, don't last forever. And so if we just let this reaction continue to happen, eventually we're going to come to equilibrium. So notice that the overall reaction is the sum of the two half reactions, just like we learned before in terms of how to balance overall redox reactions. And this reaction is going to eventually come to equilibrium. And when it comes to equilibrium, the flow of electrons in this direction and the flow of electrons in this direction are going to be equal, and so there's going to be no net voltage difference between the two half cells. And if there's no net voltage difference between the two half cells, then our battery can't do any work. And that's when your cell phone goes dead, your iPad goes dead, your laptop goes dead, you can't use your calculator anymore because it goes dead, and you have to recharge your battery. So when an electrochemical reaction or any reaction comes to equilibrium, it cannot do work anymore. That means, of course, that if the cell is out of equilibrium, electrons will flow through the external circuit and we can do work. And so the type of work we're doing is electrical work. We are pushing electrons through a circuit, that's electrical work. It's very necessary to have this salt bridge here because if we don't, we're going to build up charge and we won't get electrons flowing through the circuit. So even though the reaction's not actually at equilibrium, we'll have a high enough resistance in our cell if we build up too much negative charge over here. So we have to have this salt bridge to equalize the charges. If you have some other way of equalizing the charges by somehow putting the two cells into contact through some kind of solid conductive material that allows ions to go back and forth between the two half cells, you can in fact have a cell that doesn't contain any electrolyte. So in other words, you can have dry electrochemical cells that don't have any water or any solution in them. And this example of this are solid state cells like nickel cadmium batteries that power your cell phone, that power your laptop, are very ubiquitous in the electronics industry today.